Hello, in this video we're going to be talking about Wien's law. This is the second equation in 8.2, and it's going to describe the spectrum of light emitted by a black body radiator. We get these interesting curves that we'll talk about that show how much of all of the different frequencies or wavelengths of light gets emitted by an object based on its temperature when it is glowing with radiation. So still in 8.2, thermal energy transfer here. Now we're looking at the spectrum of light. So we've been talking about black body radiation, this idea that warm objects emit energy, emit heat through light, through EM radiation. And the last thing I think we talked about when we were talking the Stefan-Boltzmann law was this idea of emissivity. And the idea of a perfect emitter of radiation, which we call a black body radiator. This is like we do in physics a lot, sort of an idealized thing, but again, a lot of the times we can approximate objects, especially astrophysical objects like stars and planets, as black body radiators, and our results are pretty good. So we assume that the emissivity is one, that is, this thing is emitting as much radiation as it possibly can for the temperature that it's at. So we use 1 for emissivity in the Stefan-Boltzmann law. But the thing we might want to look at is the type of light being emitted. So the sun is a black body radiator, is emitting a whole lot of energy as light, and we know it's mostly visible light. The sun is sending out all the colors of the rainbow, Roy G. Biv. There's some UV radiation that comes from the sun. But the Earth is also a black body radiator. The Earth is giving off energy as light, but the Earth is not shining visible light out into space, not in any meaningful amount. It reflects a good amount from the sun, but it's not because of its temperature sending light off into space in the visible range. What it's doing is it's sending a lot of infrared light, a lot of heat. So why does that happen? There is a law for this. But the idea is there's a spectrum. It's not just one frequency, it's not just one color. The sun is not like just green. The sun is giving off all of the colors of the rainbow, plus a whole lot of other stuff. Again, ultraviolet, infrared, etc., etc. So the type of, the spectrum, we call it, of radiation that comes off depends on temperature. So here's what that spectrum looks like for the sun. This is from the sun. We can see what it's showing on this graph is intensity versus wavelength. This, believe it or not, is a graph you're going to see a whole lot. This is a black body radiator curve, and this shape of the graph, which looks crazy, it's got this quick peak and then it kind of slowly falls off. All black bodies emit radiation in this general kind of like distribution. So get used to seeing this and even drawing it, this quick peak and then a slow kind of drop off. But what it's showing is how intense the light emitted by the object is at different wavelengths. So here we have the visible light region of the spectrum, and what this is showing me is if we did some kind of fancy area under the curve stuff, that about 44% of the energy given off by the sun through light is in the visible light region. So compared to all the others, more of the sun's energy comes off as visible light than anything else, which makes sense. The sun shines all kinds of visible light that we can see with our eyes. And interesting, the sun peaks kind of close to green. The sun does not appear green though, because it's giving off a whole lot of all of the different colors of the rainbow, which we know or maybe remember appears to our eye as white light. The sun, believe it or not, is white. It appears white. If you look at it from space, you would see it looks just like a bright light bulb or something. It's like a source of white light, all the colors of the rainbow. Now it looks, yellowish, orangish, reddish in the sky because of effects from the atmosphere that we will talk about one day. But if you go to space, you will see the sun and you will see a blinding, very bright white light. But we can see the sun also gives off a good chunk of its energy in the infrared range, less and less as we get to longer wavelengths. And, maybe 7% of the sun's energy comes off as ultraviolet as we go beyond violet here. and this is the radiation that will give you a sun tan or sunburn, depending. So this is the curve that will kind of talk about that intensity distribution. It's very, again, a very strange kind of curve. The mathematics of plotting this curve, like, you would be very hard pressed to write an equation, that you could put into Desmos that would make this curve. It's a very statistical thing. This is almost a type of statistical distribution, which is very interesting and was very confusing for a long time, which we'll come back to perhaps in quantum physics. But the good news is you don't really have to worry about the math of this curve. You just have to know generally the shape of it and be able to kind of sketch it. And the other thing that's going to be really important is where this peak is. And that's what the equation we're going to talk all about is where is that peak? Because that more or less will tell me what type of light is being emitted the most. So for the sun, it's in the visible range, and it's pretty much smack in the middle. So the sun appears white in the sky because it's giving off a fairly even amount of all of the different colors. This explains why when things are really hot and giving off light, you see different colors. A candle flame, for example, is blue at the bottom because it's the hottest there. And it turns out the hotter you are, the more shifted this peak is going to be. So for a candle flame, that peak is more like over here at the very bottom, at that hot part of the flame. And so we get more blue than any of the other colors, and the bottom of that candle flame appears blue. Whereas over here, it's not quite so hot, so it appears more like red. So this is going to explain the difference between, blue hot and red hot and white hot and all that stuff. So to get into it, here's a couple different curves, and you can see based on temperature, they look very different. Number one, the high temperatures are much taller, which should make sense. The intensity is going to be much higher. The Stefan-Boltzmann law would explain that as temperature goes up, the total power emitted goes way up. So these things get much taller because it's giving off much more energy, but also the location of the peak changes, and that's what we're going to care about. Where is this peak? Something that's 3,000 Kelvin peaks down here in infrared. 3,000 Kelvin would maybe look red. We have some visible light in the red region, so you could see this as like a dark red color. This would be something that's glowing like red hot, and you see like this kind of dull red glow to it because the part that you can see, it's giving off some red and orange light. Same thing with something 4,000. This would be brighter, but it would also still probably appear mostly red. It's giving off a little bit of everything, but it's giving off more red light than anything else. And as we go up and up and up, we get to something over here where now this is going to start to appear like white hot. It's giving off a sort of even amount of all of the different colors, and the peak is right in the middle of the visible range, which means to our eye it's going to appear white hot. And if I go even further and get to the point where the peak is way over here, even further, that's where it's going to start to appear blue hot. So this peak changes as temperature goes up. It looks like the peak moves sort of backwards on the graph to shorter wavelengths. So here's another way to visualize that. This is how you're going to do it on an IB exam, say. They will give you questions like this. They will give you these graphs and what you're expected to do. The only number you really need from these graphs is to figure out where the peak wavelength is, or where the maximum on the graph is in terms of the wavelength. So we call this the peak wavelength, the wavelength that gets emitted with the most intensity. And you would just read it off the graph. So you want to read this peak wavelength, you would take your ruler and you would find the peak and draw a line straight down from the peak to the x-axis, because the x-axis is wavelength. So for this one, let's say 12,000 degrees, the maximum wavelength, the peak is right here. And so the maximum wavelength would be, I don't know, 0.23 or something. We would read it off the graph there, 0.23 micrometers, something like that. For this one, I would read off the graph, it's closer to 0.3. For this one, I would read off the graph, it's maybe 0.37, whatever. So that's what you're going to do to get this number. And this number, the peak wavelength, is what we're going to care about in the equation. So here you go. It is called Wien's displacement law. It describes this relationship between wavelength and temperature. And it turns out they are inversely proportional. As temperature increases, the peak wavelength decreases. This is a constant here. They write it in the equation. It's like not something you need to look up in the front of the data booklet, which is interesting. But there you go. They also very nicely remind you, because it's easy to mess this up because you're usually going to have stuff like micrometers or nanometers, and you might not always be given temperatures in Kelvin. So they put in the equation meters Kelvin so that you know what unit should be going into the equation. So it's really a very simple equation to use. If you know the peak wavelength, you can figure out how hot the thing is. And if you know how hot the thing is, you can figure out what the peak wavelength is. You just have two variables. You'll know one, you're solving for the other. So lambda max, remember lambda is the symbol for wavelength. That is the peak wavelength. We want to use meters in this equation. And capital T, of course, is temperature in Kelvin. This constant basically has meters in Kelvin baked in. So those are the two equations that describe how a warm object gives off light. We have the Stefan-Boltzmann law, which tells us that the total amount of energy in a given time, or the power, depends on the size of the object, the temperature of the object, a constant, and its emissivity. And the color of the light that gets emitted, or where the main chunk of the light gets emitted, the region where this peak is determined by this new equation, Wien's law. So between the two of them, there's lots of things you can figure out about black-body radiators, and we will practice them together. So there you go. Those are the two equations to know for the unit, and we'll work on them. Have fun.